Welcome to session 2 with focus on asset allocation with stocks, bonds and bills. The learning goals for session 3.2 are: you should be able to build an optimal portfolio with stocks, bonds and bills. You know how to compute the optimal risky portfolio, and students are also able to follow the required steps to find the optimal allocations for the complete portfolio. The Sharpe ratio. When choosing a capital allocation between risky and risk-free portfolios, investors naturally will want to work with the risky portfolio that offers the highest reward to volatility or Sharpe ratio. In this example, it would be the capital allocation line of B, which actually outperforms the capital allocation line of A on every single point except at the intercept. Another way to put this is that the best risky portfolio is the one that results in the steepest capital allocation line. Steeper capital allocation lines provide higher excess returns for any level of risk. Therefore, our next step is the construction of a risky portfolio combining the major asset classes that provide the highest Sharpe ratio. The opportunity set of the debt and equity funds and two feasible capital allocation lines. What if our risky assets are still confined to the bond and stock funds, but we can now also invest in the risk-free T-bills yielding 5%? The first possible capital allocation line is drawn through the minimum variance portfolio A, which is invested 82% in bonds and 18% in stocks. Portfolio A's expected return is 8.9% and its standard deviation is 11.45%. Portfolio B invests 70% in bonds and 30% in stocks. Its expected return is 9.5% and its standard deviation is 11.7%. The Sharpe ratio example. With the information from the previous slide, we can calculate the Sharpe ratio SA, which is equal to the slope of the capital allocation line A, and the Sharpe ratio SB, which is equal to the slope of the capital allocation line B. The Sharpe ratio A is calculated by taking the risk premium of 3.9% divided by the standard deviation of 11.45% equal to 0.34. SB is calculated by the risk premium of 4.5% divided by the standard deviation of 11.7% equaling 0.38. As you see, this slope is steeper than the slope of A. Debt and equity funds with the optimal risky portfolio. From the previous slide, we realized that the portfolio B has a higher Sharpe ratio than portfolio A. But why stop at the portfolio B? We can continue to ratchet the capital allocation line upwards to the greatest extent possible, which is where it ultimately reaches the point of tangency with the investment opportunity set. This yields the capital allocation line with the highest feasible Sharpe ratio. Therefore, the tangency portfolio labeled P is the optimal portfolio to mix with T-bills. We can read the expected return and standard deviation of portfolio P from the graph with an expected return of 11% and a standard deviation of 14.2%. To calculate the Sharpe ratio, we simply use the formula defined by the risk premium, which is about 6% divided by the standard deviation, which is about 14.2%, resulting in a slope of 0.42. In practice, when we try to construct optimal risky portfolios from more than 2 risky assets, we need to rely on a spreadsheet or another computer program. Calculating the optimal weights of portfolio P. How could we calculate the components of portfolio P if we do not have a graph where we can read the expected return and standard deviation? As we know from previous sessions, the expected rate of return of a portfolio is the sum of its weighted returns. Knowing that the expected return of debt is 8% and for equity 13%, we can simplify the formula. The same can be applied for standard deviation. The formula with 2 risky asset classes is with a standard deviation of debt equal to 12% and a standard deviation of equity equal to 20% and the covariance of 72%. The objective is to find the weights for debt and equity which would result in the highest slope of the capital allocation line. To get there, we maximize the Sharpe ratio by finding the optimal weights of debt subject to the sum of the weights invested in equity and debt equal to 1. After having applied the first order condition to the Sharpe ratio, the solution for the weights of the optimal risky portfolio is given by the following formula. Notice that the solution employs excess returns denoted with a capital R rather than total returns. The weight of equity is simply the difference adding up to 100%. In this given example, with expected returns for equity of 13%, standard deviation for equity of 20%, expected return for debt 8%, standard deviation for debt 12%, a risk-free rate of 5%, and the covariance of 72, we actually receive a weight for debt of 0.4. As we know, it has to add up to 1, so the equity portion is simply 1 minus 0.4 equal to 0.6. Knowing the weights of equity and debt for the optimal risky portfolio P, we can calculate the expected return and risk given by its standard deviation using the general formulas. By entering the input data into the formula, we'll find an expected return of 11% and a standard deviation of 14.2%. These are the same results as we have previously found from reading the graph. Knowing the standard deviation, we can calculate the Sharpe ratio of portfolio P. Notice that this slope exceeds the slope of any of the other feasible portfolios that we have considered. It must be the slope with the best feasible capital allocation line. Determination of the optimal overall portfolio. Now that we have constructed the optimal risky portfolio P, we can use its expected return and volatility along with the individual investor's degree of risk aversion A. To calculate the optimal proportion of the complete portfolio to invest in the risky components. Assuming an investor has a coefficient of risk aversion equal to 4, we find the overall weight of portfolio P and the weight of T-bills by using the general formula discussed in the previous session. This one is maximizing the investor's utility. So investors will invest 74.39% of his or her overall wealth in the risky portfolio P and 25.61% in T-bills. The proportions of the optimal complete portfolio. With the results computed on the previous slide, 74.39% invested in portfolio P and 25.61% invested in T-bills. The corresponding proportions of invested stocks and bonds can be calculated as follows. We can actually calculate the complete portfolio by using the previous general formula for the expected return. It's simply the weight of the risky portfolio times its expected return plus the weight of the risk-free portfolio times its risk-free rate. This equals 9.46%. To compute the standard deviation of the overall portfolio, we actually multiply the weight of the risky portfolio times its standard deviation equal to 10.56%. The Sharpe ratio is calculated by using the risk premium of 4.46% divided by its standard deviation equal to 0.42. Once we have reached this point, generalizing to the case of many risky assets is straightforward. Steps to follow to arrive at the complete portfolio. Let us briefly summarize the steps we followed to arrive at the complete portfolio. First, we specified the return characteristics of all securities: expected returns, variances, covariances. Second, we established the risky portfolio by using the asset allocation theory. We calculated the optimal risky portfolio P and its weights for equity and debt, and we calculated the properties of the portfolio P by calculating the expected rate of return of the portfolio, its standard deviation, and its Sharpe ratio. Third, allocate funds between the risky portfolio and the risk-free asset. This process is called the capital allocation. We calculate the fraction of the complete portfolio allocated to P, the risky portfolio, and the risk-free assets. We calculate the share of the complete portfolio invested in each asset and in T-bills. We are at the end of session 3.2. After having carefully studied the slides and relevant chapters in the book, please start with the review questions.